We're going to talk about the atmosphere. To get started, I'd like you to try this little exercise. We want to try to predict how the temperature varies throughout the atmosphere. So on the x-axis, we have temperature. On the y-axis, we have altitude. And just for interest, you can see a few items there, like Mount Everest or the typical altitude, cruising altitude for commercial aircraft, another height for supersonic aircraft, and then 100 kilometers is the Kármán line. It's the edge of space, if you will. Of course, there's no real edge, but just a typical reference point. Okay, so what I'd like you to do is to get out a piece of paper, so just take 30 seconds, and just draw what do you think the temperature looks like as you move up from sea level up through the atmosphere. Okay, does it increase, decrease, does it change, does it go back and forth, is it constant? Just pause and take 30 seconds to do that. Okay, so this is what it looks like. There in the red on the right. Probably different from what you might have thought. This first part, though, you may have got right. So what happens as we move away from the ground, up from sea levels, we go up in altitude, the temperature decreases. We've all probably experienced this as we've gone up into mountains or other high altitude places. Definitely feel a decrease in temperature. Most of the atmosphere is here in these lower layers of the atmosphere called the troposphere, and pretty much all of the water vapor. As we move past that, we move into this part of the atmosphere where the temperature is relatively constant. You can see that here, right? This is the isothermal layer. Temperature is constant as we move up. And then as we move past that, actually the temperature starts to increase again. This first part here, it's the ozone layer, and that's heating up because the ozone can trap the UV rays from the sun. And because there's a temperature inversion, we've got warmer air above cooler air. It's very stable. So this region here is a very stable part of the atmosphere, much less turbulence or other weather effects, in part why we fly at these higher altitudes, but only in part. And then notice that it cools back down again in the mesosphere. And as we move up into the thermosphere, off this chart, it actually heats up again. In fact, it can heat up to really high temperatures, even as high as 2000 degrees Celsius. Now, that seems a bit surprising, right? If the temperature would be so high. So we have to think about that. What does that make sense? Well, it's getting really high because it's also absorbing a different spectrum in the sun, right? Higher energy UV or X-rays are being absorbed at those higher altitudes. But you wouldn't feel hot, right? Why is that? Well, remember, temperature is a measure of the energy of individual molecules, in this case, air molecules, right? It's a measure of how fast they're moving around. That's not the same thing as how warm I would feel if I was sitting in there, right? That's a function of the heat transfer. But if I'm at these very high altitudes, each individual air molecule is very energetic, high temperature, but the density is so low, these molecules are so spread out, there's so few of them, that as they bounce off me, there's very few collisions, very little heat transfer. So I would still feel I could survive there, but I'd be very cold, right, without some special suit, even though each molecule has a lot of energy. Okay, well, so we're talking about altitude. I want to understand a little bit about how one measures altitude. So be thinking first, just take a minute to think, how do you measure altitude? And when you measure that altitude, what are you actually measuring, if that makes sense? So maybe take a minute here while I'm getting ready here and just think in your mind, do you have any devices that measure altitude and how do they work? One device is called a radar altimeter. Okay, and a radar altimeter is just going to bounce radio waves off the ground. Okay, going to bounce radio waves. So if I'm at some altitude, I'm going to send this off to the ground, and I can measure the return time And, then from that I can figure out how high I'm off the ground. And what am I measuring here? What I'm really measuring is not necessarily altitude per se, or a form of altitude. This form is what we'd call height above ground level, or AGL. Right? Because I'm just measuring how far it takes to bounce off the ground and come back. So if there's different changes in elevation, that's going to affect what I read as my altitude. So that may or may not be desirable. Sometimes we want to know just how far we are off the ground and we don't care about the absolute altitude. Other times we may want something that's doesn't have so much variation with the ground. Another device that you may be familiar with, and you may have devices that use this technique, is called a pressure altimeter. So this uses a local reading of pressure. So, some smart watches or other type of devices do this kind of thing, right, where they can measure the pressure. And then from that, we're going to calculate an altitude, generally from a model of the atmosphere. That's something we'll talk about in a minute. So this is basically a model. We get pressure, and from the pressure we could look up in a table or from a calculation what's the altitude that corresponds to that pressure. But therein is the problem, right? Because the pressure doesn't necessarily correspond exactly to an altitude. Weather is going to cause pressure fluctuations. Just the variations from day to day. Lots of things can affect what pressure corresponds to what altitude. So we're not necessarily getting a true altitude. What we're getting is called pressure altitude. So if I want this to be really accurate, I need to calibrate this periodically. And some devices, right, will have that capability. If you're at a known altitude, you'll calibrate your device. And then as you go on your hike or whatever, then your altitude measurements are going to be pretty accurate, hopefully, right? Because it's going to be very good at finding those differentials in pressure. And if you started from a known altitude, then you'll have a much more accurate altitude throughout your measurements. Of course, that could still change, right? If the weather quickly changes, those may still be off. An aircraft, of course, does this frequently through air traffic control. It's going to get updates so that as it measures pressure, it's measuring an accurate altitude. Another common technique that we're all familiar with is the global positioning system, GPS. This uses satellites, and to get a good altitude reading, we need at least 4. And kind of like the radar altimeter, but without having to necessarily bounce those, in the same way, we have known positions of satellites, and there are radio waves that are coming back and forth, and so we can measure those passage times, and that will give us a altitude relative to sea level. So this is going to give us a geometric altitude. Okay, which means the height above sea level. There are, of course, problems with GPS because, again, we're bouncing these radio waves. They can reflect off buildings, they can reflect off trees or the terrain, can cause some inaccuracy. In general, when we're using GPS, our horizontal location is much more accurate than our vertical or altitude. It's harder to resolve that, as you might imagine, given the location of satellites generally above, but hopefully some maybe more to the side as well. Okay, so if we can measure altitude, we already know how temperature varies throughout the atmosphere. We now want to know how pressure varies throughout the atmosphere and how we would compute this. So to do that, we are going to go back to a very simple hydrostatic model, something you've done in fluid mechanics. So let's take this point in our atmosphere, which is some generic point. I'm going to put this little cube, infinitesimally sized cube, and look at the forces that are acting on it in a somewhat idealized way. So over the bottom surface, there's going to be pressure, and it's going to be acting over some small area. We'll call that area dA, all right? So pressure times my area gives me a force. So there's a force on the bottom of this cube. There's also going to be a force on the top of the cube. And the pressure, because we're trying to figure out how it changes in altitude, implicit is the assumption that the pressure changes in altitude, right? So the pressure is potentially different here. So we're going to say it's pressure plus some change in pressure, and this is just a cube, so the area is the same, and pressure is always pushing in, right? We're going to assume that the pressure doesn't change at a given altitude, so on the sides of these cubes, the pressure is the same everywhere, so those will all cancel out. We also have weight, right? In the, let's take the center of mass of this little control volume here. This is going to be a weight force. So weight is going to be related to the density of my fluid, air in this case, times the volume. So that's my mass, and then I multiply by gravity, right, to get the force. So rho dV, again, that's my density, times the volume gives me the mass of that fluid, and then multiplied by g is the weight of that cube. So if we just do a force balance, we're going to see if we take, well, let's just do it. Got P dA minus P plus dP dA minus rho g dV equals 0. Sum of the forces equals 0 if we're in equilibrium, a static equilibrium. And if we simplify that, we get that dP equals minus rho g dH, where dV is just h times dA. So what do we got here? Well, we've got a way to relate pressure and density, but remember that we really wanted to relate to temperature. Temperature was a thing we knew. We had some profile of temperature, so if that's known, we need to now relate that to pressure. So we can use the ideal gas law. Remember that pressure is rho RT, so this relates pressure to density and temperature through a specific gas constant for the air in this case. So we're going to plug this in here for density and then do some simplification. So we're going to get dP over P, we're going to pull the P to the other side, equals minus G over RT dH. All right, so this is something we could integrate. I could put an integral, and we can integrate this across the atmosphere. Everything on the left is pressure. Everything on the right are things that vary with altitude. R is just a constant, so that can come out of the integral. T varies with altitude, but that's something that we know. We just saw a plot of that. We can tabulate that. G is the tricky part here. In general, of course, G does depend on H. But if we leave it in the integral, it's a bit of a pain. And so a common convention is to, let's take G to be the sea level value of G, the acceleration of gravity. What that means, though, is that if we do that, that our H is no longer really the geometric altitude. It's what's called the geopotential altitude. But if we do that, then integration is really easy, and it's a very small difference. You know, all the way up to 65 kilometers even, the difference is less than 1% in terms of geopotential altitude versus geometric altitude. So this is commonly done in tabulating the standard atmospheres because it makes things much easier. You can see a little more detail in the text if you're interested. So this is what's done in what's called the International Standard Atmosphere. It's an idealized atmosphere. It's steady state. We have these linear gradients. And you'll see here this figure. This looks like what we saw before, right? The decrease, isothermal, increase, isothermal, and then decrease. But now we've got some numbers here. So what we have here is that from 0 kilometers to 11 kilometers, the temperature decreases by 6.5 kelvins per kilometer. So that's this negative slope here. And then there's a constant, right? 0 gradient from 11 to 20. So from 11 kilometers to 20 kilometers, the temperature is constant. Then there's a +1 slope, +2.8, and so on. Okay, so this is how the standard atmosphere is defined. It actually is defined all the way up to 1,000 kilometers, so it becomes a little bit more complicated and is not quite as useful generally. So that's accurate. And so given these temperature and given a starting point sea level properties, we can integrate. We can integrate and get pressure variation throughout the atmosphere, and then using the ideal gas law with pressure and temperature, we can get density variations throughout the atmosphere. And again, this is done in a bit more detail in the text. Here, for our purposes, It's not too important, those exact details, but rather we understand the concept. So this is basically a table, and then there's a bunch of equations. Those integrals that we looked at, they become relatively simple integrals that we can do. But doing this in this piecewise manner is still a bit cumbersome. So there's this curve fit that we often like to use. This comes from Mark Drilla, and there are two fits here. One is a fit to temperature, and so this is the graph on the left. The dashed line is the exact standard atmosphere, if you will, and this blue is a curve fit. It's this expression here, and you can see that it agrees really well up to, I can't remember exactly, about 45 kilometers. So for transport aircraft, we're here at more like 10. We're well under this range. If you want to do rockets, this is probably not the, well, most of the atmosphere is in this range anyway, right? If we care about aerodynamic things, once we get past here, the atmosphere is pretty thin. So this works well for a lot of aerospace applications. And then pressure, you can see also a really nice fit up to about the same. Still a pretty good fit going forward, but the temperature is no longer a good fit. So with temperature and pressure, we can just use these equations instead of having to use this table and try to have a bunch of if-else cases. We can put this in just a couple of lines of code here, plug in an altitude, get a temperature and pressure. From ideal gas law, we get a density, and that allows us to predict our properties in the atmosphere as a function of altitude. Well, there are other properties, of course, that we would want to know, to use. A few common ones are going to be the speed of sound. Okay, it's given by the square root of gamma RT, and A is the speed of sound. Gamma is just a ratio of specific heats. For air, gamma is 1.4. R is a specific gas constant, and T is just temperature, which we know. R is a specific gas constant for air, is one we would use. Another one we might use is viscosity. And this is often computed by Sutherland's law. I'll write it this way. It's beta times T to the 3/2 over T plus S. This is a simplified version here. You can look in the book for a little more detail here, but beta and S are just constants. The important point here, though, for us is that speed of sound is just a function of temperature. These are constants. Viscosity, just a function of temperature. These other things are constants. So since we already know the temperature profile, we also know how the speed of sound varies. We know how viscosity varies throughout the atmosphere. Convenient way to do this is to look at some of these tables here. So let's go to this website real quick. I'm going to switch to Safari. Like I said, you can easily write this in a small amount of code, but these calculators are often convenient. So if you just search standard atmosphere calculator, Google, this is going to be things going to come up for you. So let's say, okay, this here is in feet. Let's say we just go to meters. We can pick different units, we can plug in what we want. Let's say we want 10,000 meters, and you can see that the temperature, pressure, density, speed of sound, dynamic viscosity is giving me all these things, and as we change the altitude, it's going to, we can put it back to 0, back to sea level. It's going to give me different properties, so I can get values for all of these. This is very convenient to look these things up. Okay, just to recap here on the different altitudes, we talked about, I think each of these, but I just want to refresh here and make sure we use it. Geometric altitude, that is your geometric height above sea level. That's maybe what we usually think of as our altitude, but as we've seen, the things we measure aren't always actually exactly that. This is the height, absolute altitude from the center of the Earth. We'll use this more when we get into rockets, less relevant for aircraft where, our variation of altitude is much, much smaller compared to the radius of the Earth. So that's not important, but for rockets, especially as we get out into space, this is an important one. Pressure altitude, in words, or another way to say it, it's the altitude in the standard atmosphere with the same pressure that we measured, okay? So in other words, we just talked about how the standard atmosphere works. If I'm at some spot, I'm gonna take a pressure reading, and from that pressure reading, I can then do that sort of inverse table lookup to see what my altitude is. And as we've seen, of course, that's not gonna be perfect, right? Because this is just a model of the atmosphere. It's gonna be good with changes, much better with changes, but less accurate unless we calibrate it. So it's always important pressure altitudes to do calibration. Geopotential altitude, we also briefly talked about. It's an equivalent altitude using a constant acceleration of gravity. Acceleration of gravity. So that was just to make the integrals easier. So the reason why we need to bring this up is that when you use the standard atmosphere, the altitude that you get is not actually the geometric altitude, it's the geopotential altitude. But as we mentioned, for most aerospace applications where we care about aerodynamics, where we really care about these fluid properties, the difference is really, really small. So it's not a big deal. Okay, so the last thing I want to talk about is that, of course, the standard atmosphere is a simplification. Temperature is not the same at a given altitude all around the world. It's a useful thing as we talk about aerospace applications because we're moving up in these much higher altitudes where things won't vary quite as much. But as we get closer to sea level, or if we need more fidelity, we want to use a better model. And these exist. I'll just show you one. For example, this is a nice, cool visualization. Here's some kind of real-time data around the world today. You can see a little hurricane. I think every time I've shown this, there's been a hurricane of some kind every year. But over there in Texas, you can change it. This is just showing wind. So here's the temperature. See how temperature varies. Around the world, we can go up to higher altitudes. This is at sea level. And this is a pressure altitude that it's showing here. So we can go up to higher altitudes and see it's much more uniform than it is towards sea level, but of course there's still variations. So anyway, this is kind of a fun little visualization you might want to look at. And there are various databases that you can get more comprehensive altitude data if you need much higher fidelity. Okay, that's it for today.